All right, 5.2, applications of exponential functions. I'm going to start this with looking at not really the COVID virus, but a simulated virus situation. So I want to take you over to the left-hand side and explain to you all these different things over here. So applications of exponential functions. We've got some function, which is function notation, p of t, equals p sub 0. And then a is the base with the exponent t is our variable. See how t is in parentheses here and t is up here? That's our variable. So we've changed to x, changed from x, so that we're looking now at time. So we're looking at applications of real life things, things that happen over time. So p of t means, and we're calling in this case population, so p for population, so population at time t. P sub 0 is the initial population when time equals 0. That's why it's sub 0. And A is the base. If A is a number greater than 1, then it represents growth. If it's less than 1, but still positive, it represents decay. So my first example over here, I'm going to call I of t being the infected number of people at time t. So I for infected. So let's say that we're going to some big gathering, some big party, and people don't know they're infected, but they go, and we have a function that represents the infection rate. And let's say that I of t equals, we're going to say time is in hours. So we're talking about some party that's 12 hours long. It's an all-day event. And let's say that I of t, we're going to start with 3 people being infected initially. So 3 people are going to be the initial quantity of people that come infected. And then we're going to have a transmission rate of 2 to the t. So what that means is that our infected number of people is going to grow every hour by 2. So these are people that the first 3 people come in contact with, and then the next people come in contact with over and over again. Let's see what happens after 12 hours. So how does that work? That means that, and this is a really large party, so think of it as like a festival where you'd have a huge number of people, because this is going to grow really quickly. So let's start with a chart. Let's do time is going to start at 0 hours, and then we'll see what happens at 1 hour and 2 hours and 3 hours, and we'll look at 12 hours at the end, but let's just start there. So time is going to be in hours, and I of t is going to be what happens when we plug in 0 and then 1 and then 2 and then 3. I want you to get a feel for how this works so that it doesn't just seem like random numbers that don't make sense. I want it to make sense a little bit at least. So at 0 hours, this is our plugging in 0 here like we did with our graphs to find out that starting value. And the reason that 0 is important is because when we put it up here as the exponent, it becomes, and here's our actual function, 3 to the 2, 3 times 2 to the 0 power. Note that the 0 only applies to the 2. So this is actually 3 times 1. So in the first hour, in the 0 hour, that's just the 3 people. So that's our initial, that's why this is called the initial condition, because nothing has happened. 2 to the 0 is 1. Nothing changed with the exponential function at the initial 0 time. So this becomes 0, 3. This is the hour, and this is the number of people infected. So our number of people. In the first hour, those 3 people come in contact with 2. So we have 2 to the first power. So I'm taking my function, I'm putting 1 in for t. This is 3 times 2 to the 1. That is 3 times 2. That's 6 people are now infected. At 2 hours, we've got 3 times 2 squared. So we're putting t in for, we're putting 2 in for t. Here it is. That becomes 3 times 2 times 2. There's 2 2's. That's 6 times 2 is 12 people infected. At 3 hours, we've got 3 times 2 to the third power. Again, the 3 is always 3 to the first. 3 never changes because this is 3 to the first power. The t is only on the 2. I make that point again and again because students often try to expand that exponent to everything. So this is now 3 times 2 times 2 times 2, which is this value times 2, which is 24. So that's 6 times 2 is 12, times another 2 is 24. 24 are now infected. So you can see what happens is at an exponential rate, the growth of 2, at every hour, it doubles. There's another 2 added every hour. So the next one's going to be 3 times 4 2's, and then 3 times 5 2's. There's one more 2. This doubles the previous example. This doubles the previous example. It just keeps happening over and over again. And dot, dot, dot. If we have 12 hours, we're going to have 3 times 2 to the 12th. And at that point, we take out our calculator to find out what 2 to the 12th is because it's really gigantic. Let's see what that is. So here's our calculator. We've got 3 times 2 raised to the power 12. And that's 12,288 people. So that's going to be 12,288 people infected. Now, is that realistic? No, it's not realistic. Let's think about the reasons for that. Number one, the 3 people might have infected these 2, and then the 3 people might have infected more people over the hours of the party, so if they didn't leave. But these 2 people probably didn't infect anybody else because they have not manufactured enough virus to get other people infected. So this would really be the case if you change this to maybe days. But it does give you an idea of these 3 people walking around a party. They would infect people every hour. And then when these people leave the party, they infect more people. That's how exponential growth works for viruses. But you have to consider the possibilities there. In other words, this is not a wedding because 12,000 people don't go to a wedding, unless you're watching a royal get married outside and 3 people were out there. This would have to be some sort of enormous festival for this many people to be infected. You'd have to run into new people who aren't infected. There's all kind of things we could talk about if we were in person. I'm sure that would be a fun argument to have with people. But you can see how quickly exponential growth occurs because every time you change the time to a new time, you multiply by this growth factor, which is 2. If this was a growth factor of 3 or 5, the number would have been really huge. We could put that in a calculator just to see. If we did the same thing 3 times, but we changed the base of 5 to the 12th, then you've infected like the entire world's population, if that were such a thing in 12 hours. So certainly not a possibility in 12-hour span. But it does give you an idea of why everybody in the media was talking about flattening the curve. Because what they wanted to do was change this number, the growth factor, from 2 to 1. If you change it to 1, you're here. We have 3 times 1. You haven't really changed the number of people infected. So that's what they were trying to flatten the curve instead of making it go up in an exponential kind of graph. So this equation works for anything. You can see on the side I've written it as P of t equals the population at time 0, the base, and then this right here is the variable. looks like there's a bunch of variables in this scenario, but A is the base and P sub 0 is the initial quantity. So it's the quantity at time 0. And this equation works for a whole lot of things. It works for also radioactive decay, written in your book as amount, that's what they call it, amount of whatever it is you're looking at time t is the amount initially started with times the base to the exponent. So this would be how the book writes out radioactive decay. But if it was decay, then this A is going to be between 0 and 1. So it would be decay if it's between 0 and 1. And then our last one, I'm going to show you right here, it will be the amount at time t, and where this is going to be continuously compounded interest. And that's going to be the amount you started with, the principal, so at time 0, and then Euler's number E, and then rate times time. So this one has an extra little thing there because we need to know how much your bank would give you as a rate. So in this case, R equals the rate of interest, and E represents Euler's constant, which is E equals 2.718281828, and it keeps going forever and ever because it's an irrational number. So Euler's constant, and your front of your book, we read about that, and you should go look up Euler's constant if you have questions about it. There are notes that you were supposed to take when you read that section of the book. He found that if you took 1 and then you added fractions to it, 1 over 1 plus 1 over 1 plus 1 times 2, 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4, and you kept doing that forever, you would come up with this number, which is 1 plus 1 is 2, this is the 0.5, and then these numbers add up to these small percentages as you go forward. So this is a natural constant of population, and this is for continuously compounded interest. This equation happens. So all of these equations look remarkably similar. They are basically the translation of an exponential function just thought about in terms of time. So we looked at an exponential function like this before, where we said we had some starting value and then we had a to the x, and this looks exactly like what these equations talk about. So let's look through some real examples and make sense out of the math. Okay, so example 1. A biologist is culturing bacteria in a petri dish. She starts with 1,000 bacteria. Don't ask me how she counts those 1,000 bacteria, but she starts with 1,000 bacteria and supplies sufficient food for exponential growth. The bacteria double every hour. So the first part of this example is finding out what the equation is. And the book shows you this kind of example where they say the equation is population over time. It's the same examples we have up here. How much we start with, 1,000, and then a to the t. So we're trying to figure out what a is, what the figure is here. Now I think in this example you could simply read it and say, well, it doubles, therefore this value is 2, and you can make that conclusion automatically. If you want to see it in math though, here's a way to think about it. If it doubles every hour, then at 0 it's at 1,000. And so we could say 1,000 equals 1,000 times a to the 0. Okay, so that makes sense. At the time 0, this is 1,000. At time 1, We've doubled to 2,000. You can see 1,000 doubling to 2,000. But we still started with 1,000 over here on the right-hand side, and we have a to the first power. So we've actually got a math equation we could solve now. You could divide both sides by 1,000 and have 2 equals a to the first power. So you've solved for a. So you could do it mathematically and solve for it if you wanted to. The second part of this example says, at what time is your population equal to 16,000? So the second question, B, is when is P of T equal to 16,000 question mark. So what we need to do is go back to this equation, except substitute in A is equal to 2, and say P of T equals 16,000, which is equal to the equation 1,000 here, times 2, which we figured out, to the T. So we're looking for T. This is our question. Time. And now that I've written it like this, we're going to ignore the function notation and solve this part of the equation. So again, I'm going to divide by 1,000. And I've got 16 over 1, which is 16, equals 1,000 divides out of 1,000. So I've got 2 to the T. If I think back to my last section, this is something I know how to solve if I can get the bases the same. So I'm going to do that and say 16 is the same thing as 2 to the fourth power. And so I now have the same base. This is at time equals 4 hours. The bacteria numbers 16,000. So 4 hours is the answer for that. So you're going to take these problems and you're going to take the basic growth or decay equation. You're going to substitute in how much you start with. You're going to figure out how it doubles or not, doubles or triples or 1.5, and then times time. And then you'll use that to puzzle out the different sorts of answers you have. So let's do another example. Okay, before I get into this example, let me just remind you what half-life is. So this second example, and the book goes through on page 406, goes through a description of radioactive decay, which I'm going to read for you because they say it much better than I do. So radioactive decay is so predictable that archaeologists and anthropologists can use it to clock how long ago an organism died. The method of radiocarbon dating depends on the fact that the living organisms constantly absorb molecules of the radioactive substance carbon-14 while they're alive, but the intake of carbon-14 ceases once the organism dies. So after a period of this many years, and this changes depending on the substance it absorbs, that material will decay into other elements over time. So carbon-14 dating, which is what we're going to do in this problem, we're doing the decay of carbon-14. So carbon-14 dating is based on the fact that it takes 5,728 years for something to reduce carbon-14 by a half. So carbon-14 has a rate of this many years, 5,728 years for half of the carbon-14 to decay into other elements. I know that sentence uses carbon-14 twice, but into other elements. So we want to rewrite this idea of how many years it takes into an equation so we can figure out what would happen. So let's think about this. Let's just make up something random. So for example, let's say we had 10 grams of something. So 10 grams of wood. All right, and this is grams. And we're trying to figure out how to rewrite this into equation. We know that if we have 10 grams of wood at the time that something died, then in 5,728 years, we would have 5 grams of carbon-14 in the wood. All right, so that's what half-life means. It goes from 10 to 5, that's half, in this many years. So what we're looking at is if we rewrote this like the last problem, we would say we had amount at time t would be the initial amount times the A at t. We're trying to rewrite this with the information that we have. So let's see. We're saying in 5 grams happen, the initial amount was 10 grams of wood. That's what we started with. And so that's our initial amount. We're looking for A. We're looking for the base. Determine the base. So that's our goal. And so we're going to keep the A as an A, but we know that it takes, to go from 10 to 5, it takes 5,728 years. So hopefully that makes sense to you. We're trying to figure out what the base would be that makes it so carbon-14 dating works. So we solve this by getting a to the exponent by itself. We would divide by 10. And that takes us to 1/2 equals a to the 5,728. Now, this is something that neither you or I can do in our heads, but it does make sense. We're talking about half-life. So the amount is in half. We're trying to figure out what that base would be that you would multiply every year by that substance so that it reduces, and it reduces so slowly that it takes 5,728 years to do it. So let's take out a calculator and figure this out. So many of these problems will use a calculator. You will need calculators for your exponential exercises. So I'm going to clear this out. How do we get a by itself if it's raised to a power? Well, we raise it to the inverse power. We raise it to the 1 over 5,728. So that's going to be 1 over 5,728. That means root. So we write root in the bottom here. That means we need to put it in the calculator like this. These two make 1. So we have A on the right-hand side. Now we just need to take 1/2, which I'm going to write as 1/2. Oops. I'm going to write as 1/2. There we go. And I'm going to raise it to the power, and I'm going to make sure I do this right. So I'm actually going to put it in parentheses. So 1/2. That way I know that everything is going to be to the right power. Here's my power button, and I just type in this crazy power. So 1 divided by 5,728 as a power. And this gives me A is equal to 0.999879. I've chosen to make it 6 digits. I don't know how many digits the book would make you go to. If I need a specific number of digits, that's what I'll give to you. So what does that mean? Because that seems really arbitrary. Let's go back. If we say amount at time t equals, we're starting with 10 grams. So a long time ago we had this amount of wood that had 10 grams of carbon-14 in it. So we're saying we start with 10. That's our initial quantity. We're raising it. We're saying that the growth or decay factor in this case, this number is smaller than 1, right? So this is decay. So this represents decay because smaller than 1. To the power t. So this is putting it back into its function form. Initial amount times this. So after this is at 0 years, this is what we'd have, 10. In the first year, you'd have, let's do on the calculator, 10. Well, Here we go. 10 times, then we're going to take this amount right here. Whoops. Okay, I'm bad at typing. 10 times, arrow up, this amount to the first. Now they look the same, so I'm doing 10 times 0.999879 to the first power and enter, and that gives me 9.9987 9 again, and that fell off my paper. Sorry about that. So I have just a little bit smaller than 10. And then after 100 years, I've got 10 times 0.999879 to the 100 power. So I'm going to do the same thing. 10 is my initial quantity times, I'm going to go back up to this amount. That's the decay factor. Raised to the power of 100 years. Enter. And I still, look, I still have really close to 10. This would round up to 10 if you were rounding. So this is equal to 9.87972. And after 1,000 years, I'm going to have less, and after 5,000 years, I'll have 5. So let's test in somewhere in the middle. So instead of 5,700, let's test like 3,000 years and see how much we have at that point. So I've got 10. Actually, I'm going to go up here and just use this one. And I'm going to change 100 into 3,000. I've got 6.95565. And so this would be grams of carbon-14. So we had, because the time was so long, this number is really, really close to 1. But it's still, every time you multiply by another one of these, it gets smaller and smaller and smaller. It takes 3,000 years to bring it down to almost 7 grams. And if you went all the way to 5,700, you would get to 5 grams like we figured out. So you have to read the problem and figure out how you can use that to puzzle out an equation. Now this one, I made up my numbers, 10 grams and then to 5. You can make up anything because at the end it's going to equal a half, because this was about half-life. So it was going to equal a half. So some problems are harder to puzzle out than others. All right, this third example is a little bit different because in this example, we're looking at the amount of money that someone has. We have an initial principal, and then we have this extra R here. So in this case, we have to consider the rate of return on investment and times. This has 2 variables, but the rate will stay the same for every year, so it's not really a variable in the same sense. So here's our situation. Sandy is investing $10,000 in a continuously compounded account earning 4.5% interest. What will be the value of her account in 3.5 years? So number 1, this would be amazing if we could get this today. Interest rates are so low, we would never reach this. But this is our rate, our R value. So let's rewrite just underneath it all the things that we know. We know her initial investment, her principal at time 0, she has $10,000 at that 0 moment when she walks in the bank. So that's $10,000 right here. E is Euler's number that reflects what happens in an instant. So it is a mathematically figured out number that represents you looking at interest every second. what did you earn this second and the next second and the next second continuously. And the book explains all that. We've talked about that in Algebra 2. We're going to go with the equation now that we have hopefully some understanding of Euler's number from before. So read the book further if you want to find out where Euler's number came from. This is a number in your calculator like pi. So it is not a variable, it is a number that means 2.7, 1828, 1828, and the rest of the numbers I don't remember. So Euler's number, and we've got rate, which is 4.5%. We need to change it to be 0.45. Here, when you change percents and use it to calculate, you change it into a decimal. And then we need to put in time. This is the equation for any time, at any time, t. The only variable you have is t, and now the only variable I have is t. If we want to find out, using proper notation, the amount at 3.5 years, we put in 10,000 and then e to the 0.045 times 3.5. And you put this in your calculator and let it figure it out for you. So I'm going to clear everything out. I'm going to put in 10,000 times e. So e you can find above the ln button. So those are inverse functions we'll talk about when we get to logarithms. And so it takes you directly to an exponent because e's are used for exponential functions. I'm going to put in 0.045 times 3.5 years. There we go. 0.05, 3.5 years. And at the end, she would have made $1,705. So her total is $11,705.80. You would, in mathematics, you would round up to this 81, but the bank's not going to give you that penny. So you round down with numbers. I would count either correct on a math test, but realistically speaking, the bank's not giving you that 3 cents. You've got to earn it. So this represents growth because E is a number bigger than 1, 2.7, 1828, 1828. And there you go. All right, you have some practice problems to work on for this. I need for you to think logically. I need for you to think about the problem in terms of what the initial quantity is. I need you to think in terms of, is it something that should grow or something that should get smaller? When you think about this base for the exponent, I need you to think about what the rate is as far as time being in months or days. Sometimes you might need to rearrange your exponent so that it reflects the units involved. And they all sort of have this same feel to it, where you have initial quantity, the base, times time. Some of the problems that are given to you for practice, you need to use your calculator for. You can't do without a calculator, but you might need to use exponent rules in order to figure out how to put it in your calculator. So going back to this problem where we got right here, in order to get a by itself, you had to undo this power. You undo a power by raising it to an inverse power on both sides. And then this is what you put in a calculator. So those kinds of things you really have to work on paper. In order for you to have credit for this assignment, I need to see all of what you're thinking when you go through a problem. I need to see the original equation either written out in letters and then substituted just underneath with the math worked out along the way. Or something. There is not a problem where you can just write an answer. All of the problems want you to initially find some sort of base equation to start with, which includes the principal amount, the initial quantity, and then either the base to an exponent or the base as a variable raised to an exponent like this one where we knew what the time was. So all of those require work on your part in order to figure out. Any questions that you have, you should let me know, of course. Make some notes on your paper. I do not expect for you to write out the problems completely in words, but what I would like, say this was your problem example 3, I would like for you to say something like initial is $10,000, rate is 4.5%, time equals 3.5. There needs to be a list. Instead of writing everything out in words, I need to see that you found the important information and written it down, and then from there you can use it in an equation. So that's how you get credit for this assignment. If it's just a list of answers, you won't get any credit at all. These are difficult, and some of the ones that I do want you to practice on Khan Academy, you can find some great exponential problems on Khan Academy. Take it further than the ones in your book. So you'll need to be able to write things down and figure out how to work them initially here so that you can go and work the more difficult problems. All right, thanks a lot.